I think it's now going. Good morning, everyone, and welcome. And thank you for joining this webinar on ColdStream. Just for your information, my name is David Meesaros, and I'm a technical consultant in Summa on the CFD side. And I'm here together with Lieven Vervecken, with the founder of Diabatix and also ColdStream. Just some information from our side, so that you know this session is being recorded, and if you have any further questions, please feel free to put them in the chat, and then we will answer them after the session during the Q&A session. So to get started, maybe we are in Summa, and we have around 60 years of CAE legacy, mainly with MSC software. And we are basically, on a general note, we are the exclusive business partner of MSC Hexagon in the Benelux. So if you can click further, maybe this one. So we have mainly two teams at Summa. We are consisting of a sales team with 4 people, and then we also have a tech team also consisting of 4 people with different expertise and backgrounds to support our customers with their CAE engineering needs. From 2024, we are a exclusive business partner also for DDS, called Dynamic Design Solutions, and also for Diabatix. And we have partnered up together to basically showcase to you the possibilities of ColdStream, which is a thermal CFD and generative design tool. And on short, we have more than 100 customers. We are operating in various industries, such as aerospace, automotive, or semiconductor industry as well, providing supports and services to our customers. To think about what kind of customers are we talk about, think about, for example, some references in the automotive or in the semiconductor industry. And by that, maybe I would like to give the word to my colleague Lieven, and he would like to introduce to you to ColdStream.
All right, thank you, David, for that. I don't know if you wanted to add something about this last slide.
No, I technically explained it, so you can go ahead, please.
All right. Okay, good. Thank you all for everyone for joining. Pleasure to meet you all or connect with you all. I'm Lieven. I'm one of the founders of Diabatix. Also one of the, let's say, the architects of our technology. My apologies for not being able to switch on my camera just like 30 seconds before the start of the webinar. I got the system failure, so won't be able to resolve that now. But in any case, it's a pleasure to have this opportunity to showcase and explain what ColdStream and Diabatix are about. Let's say, almost a year after we started partnering up with Summa. So looking at the high level, when I started Diabatix about 10 years ago, the goal or the idea was to empower engineers to help them design beyond the imagination. This particular in the field of thermal design, thermal management. And the way we approached this was through the use of smart algorithms. We wanted to do things differently. Wanted to enable taking that next step, reaching higher power densities, reaching a design much more efficiently than the traditional way of working. And so after all of these years, that actually resulted for us in the development of ColdStream, which is worldwide the #1 generative design platform for cooling, and basically is one of the most powerful tools that you can use when assessing or when evaluating when creating a thermal design. And I will show several examples in the with respect to ColdStream, but just for you to one mistake and already passes, whether you have liquid cooling, air cooling, forced convection, natural convection, fans, pumps in your system, and so on, the ColdStream supports the full system and can help you every step along the way to find the best possible cooling solution that fits your needs. And the way, the reason why we can actually do that is or that we have that flexibility in physics, in design processes and so on, is by the way we constructed actually the platform in the backend. So if you would look at ColdStream from a high level, the way it is constructed is actually, it makes actually the combination of 5 different dimensions, 5 different building blocks. And I can imagine that many of you, or most of you, are probably familiar with this simulation engine. So this is basically, as in layman terms, you give this a geometry, a product that you have been working on, a geometry, whether or not it already contains a heatsink or not, doesn't really matter that much, but it can predict the temperatures, the resulting temperatures of your heat sources, of your electronics, and so on, given certain environmental conditions. It's basically a full three-dimensional CFD engine that can be used at high resolution, low resolution, and so on. But it predicts basically predicts performance of your product. Now, most of you probably will use this on a daily basis to evaluate designs that you manually iterate over together with colleagues to see how to further improve it. Now, what ColdStream actually enables is to couple the simulation engine with a shape generator. And the shape generator can create, basically can modify your geometry, can control your geometry, and can create anything from pins and fin structures all the way to three-dimensional gyroids that are suitable for 3D printing, or complete freeform shapes. And I will show you a few examples of that later on in this talk. But just keep in mind, you can use it for the full broad spectrum of applications that you want to tackle. So whether you're searching for an off-the-shelf component that looks like pins or fins, or whether you want to have a highly customized 3D printable design, shape generator will be able to create these geometries. Now, obviously, if you have a shape generator and you have a simulation engine, you need to have the brains that connects the two, and that's this generative design engine. So what it actually does is it takes the output of a simulation engine and together with the input that comes from the shape generator on what the cooling geometry is that was attempted, the simulation engine generates a few gigabytes of data, and it's that data that will be used internally to train a model and gradually teach the system, the system gradually learns about the behavior of your component against design changes. And with this learning process, that the design process will actually be controlled and driven and steered towards the most optimal design for you. Now you see 2 additional building blocks. On the one hand, you see here the material database. It is basically what it says. So it's a full database that can be customized, that contains a list of materials, and that makes sure that your simulation engine predicts the reality as accurately as possible. And on the other hand, very important, a manufacturing database, again, fully in control of our users of the software. And it's here that you can control what shapes the shape generator is allowed to create with during the design process. So if you're looking for a battery cold plate for automotive that needs to be that starts from sheet metal that needs to be formed, or you want to have a CNC milled heatsink, is the manufacturing database that will actually take care of that of those restrictions on your design process. And so the magic actually happens inside ColdStream. The magic happens when you combine all of these 5 building blocks together, because when you do so, you can take that next step in thermal design. And so you basically open up then a new list of opportunities, and here on the screen you see a number of shapes, a number of examples of that you can quite easily, with just a few simple clicks of the button, can generate within ColdStream. To evaluate pins, fins, serpentine channels, the gyroids, and so on. And this is only the spectrum of the standard design, as we call it. So basically, a template basis starting from a predefined shape, searching for what's the best sizing of these components. And it, as you will see in a few slides, besides this list, you also have a whole series of options for full custom designing. Now, workflow-wise, and this is a very advanced technology, and so we have been developing this for over 10 years. In the meantime, probably one of the most complex, most advanced design methodologies that you can find. But we don't expect, obviously, that our users of the platform are the same experts as we are, and so we try to make this as easy and simple as possible to use, and it basically comes down to a simple workflow that you're familiar with also from when running any other CFD simulations or any other type of analysis. So the whole process, I'm not going to give a full live demo on this. Feel free to reach out in Summa if you have that interest about that. And so, but what you will see then during a live demo is that it basically starts with an import of your baseline geometry. You specify your different regions, you specify the different boundary conditions, you set the targets, and that's then really the new part. So instead of pressing here or setting, after setting the boundary condition, after a boundary condition saying, okay, let's start the simulation, the one next step that you need to take with ColdStream is setting targets, minimize the temperature on specific regions, putting a pressure constraint on the inlet pressure, imposing maximal temperature constraints on the fluid temperature, and so on. And these targets that will actually drive your design process and will help to evaluate if a design is better or not. And then within the design space that the user has that the user also controls, a new design is made. And so you see here at the bottom already a sneak preview of what a cooling jacket of an electric motor, what the input is on the left-hand side, and what then the output would be in case of a 3D printed cooling jacket. And obviously at the end, you get a CAD file as a result, a step file, which you can integrate again into your regular way of your regular tool chain and basically continue the way you're used to working. And so, so the real magic happens in these targets, and maybe already good for you to know, there are more than 20 objectives and constraints available in ColdStream that you can use in a multi-objective, multi-constraint context, where you have full control over the different weights over the different targets. So there's absolutely no limit to what you can do and to customize customize these inputs to exactly what you would like to achieve. So let's zoom in on a few of these steps. So just imagine you're designing this kind of a chip cooler, like you see here on the screen. So you have it's basically a few screws. You have a housing. Inside the housing, you have space for a cooling channel. And then all the way on the right hand side, you see here at the bottom, it's basically your heatsink. And this can be a simple model for a GPU cooler or a CPU cooler, or a liquid cooled electronics module, and very similar also for power inverters, very similar baseline model that you would use for that. And so what the first step of ColdStream, as mentioned, was importing the geometry, what you see here. Second step is specifying the materials, can be copper, aluminum, and so on here, and then specifying the boundary conditions. You see here, total power imposed at the bottom side, 500 watts, split in 3 different regions. Again, full control over how to customize this. And the same with the design targets. If you want to if you want to optimize this for a minimal temperature, simply define these 3 heat sources, the 200, 100, and 200 watts. Simply say, okay, minimize now the temperature on these heat sources with a pressure constraint on the inlet, because you don't want to end up with the pressure of several bars, especially not for this kind of a small component, obviously. Now, and then ColdStream can help you in many different ways. So imagine that this is your starting point. If you look at a regular thermal design cycle, you have on the one hand typically a, let's say, conceptual design phase, and then afterwards a detailed design phase. It's exactly that way of working that is also embedded in ColdStream. And so first step, and defining the concept, means we indicate within the designs, within the model that we have built up, we indicate the space where we can make some modifications. And in this kind of example, I think many of you or most of you will be able to imagine a very classical question to ask is, okay, do I need to would a pin fin heatsink be best? Would a regular fin heatsink be best? What would be the performance if we explore some more exotic shapes like 3D printing? Do they have with the gyroids that you see here at the top? Does that offer a big advantage over pins or fins, or does that perform at the same level? So you have beginning of a design process, many questions to answer. And obviously, that's where ColdStream can come in and be of a big assistance to you. Because it's basically as simple as defining the setup once, selecting all the different variations you want to explore. And in this case, 3 different concepts. And pressing the start button, let ColdStream evaluate for exactly the same input, for exactly the same targets, for exactly the same constraints. Let it evaluate what's now the best shape. And that makes also comparison very easy, very straightforward, because each of these results, each of these designs of each of these concepts that you see are evaluated with exactly the same models and against exactly the same constraints and targets. So all 3 designs, although they look very differently from contact area, from fluid volume, and so on, they have an identical pressure drop, and they are bound by the same manufacturing methods. So you have a very objective way to compare the three concepts, and you can easily push this to more than 20 concepts for a starting phase. And so what actually happens behind the scenes with this model is actually that for every concept that you evaluate, you actually run a full optimization. Again, it's all embedded. You get the output, you see what's happening, but you don't need to worry about the full setup of these things. That's exactly the power of the generative design technology, because you end up with more than, in this particular example, more than 1,000 designs evaluated in less than 2 hours for a setup time that probably is only 10 minutes. And so if you have to answer the question, okay, are pins the way to go, or fins the way to go, or anything else the way to go, after 2 hours of computing, you will know the exact answer, and you will have left no opportunity untouched. And this is obviously very powerful in a custom design. In an early stage for a design process. Obviously, very valuable to save time when you need it the most. Because last thing you want is take a wrong choice here, go in the wrong direction, because that will be highly penalizing afterwards, when you have to correct yourself for let's say a choice you made all the way in the beginning. All the way in the beginning of a design process. So, and that's step 1. Now, obviously, you can with this first step also comes a whole bunch of additional insights. So, and that can help you understand where things, what's the advantage of each of these designs that were created, where are the disadvantages, where are the cold spots, where are the hot spots, and so on. And so, obviously, with the CFD engine embedded, the data that is here on the screen is readily available. A few clicks of the button to visualize, okay, what's now actually happening inside my component. Now that's for the standard design process, and so or the concept design process. Now imagine that you, after this concept design, you say, okay, I have here pins and or fin heatsink, and it's okay from performance, or it's not okay from performance yet. Would be best to squeeze out 10-15% lower thermal resistance. Then we basically switch to the core of ColdStream, the most powerful functionality of ColdStream, and that's the custom design functionality. That's the full generative design functionality, where instead of limiting ourselves to a certain template shape, you can actually give it the full freedom to design whatever you want to see. And so, and a good example to illustrate is the following. So let me just zoom here to the let me just pause here to the initial starting point. Voila. So imagine that you're designing an air-cooled power inverter or air-cooled power electronics module. You have a number of electronics mounted on the backside of this module. You see them here on the bottom right, and that generate heat and needs to be cooled down. On the bottom side, you have, or the cooling side, you have two fans characterized by a fan curve, and an open space afterwards that you can use to create a shape. The main boundary condition manufacturing-wise is it needs to be die castable, and this particular example was an automotive power inverter. So obviously you need to have something that is mass manufacturable afterwards. You see in the picture here at the bottom left that the full die casting process is characterized by a number of parameters. By specifying these parameters and the bounds to these parameters, like minimal channel width, maximal channel width, draft angle, and so on, you are in full control over what is manufacturable and what is not within ColdStream. So step one, importing the geometry. Step two, specifying the boundary conditions and the materials. Then last step, specifying the targets, and that's then minimizing the temperatures while respecting the fan curves. And then last thing to do is press the start button. And so what you actually now see on the screen, voila, in the video is a visualization of the design process that is ongoing in the backend. So you see actually every frame of this video is one iteration done by ColdStream. Voila, and gradually you see it evolving then to a structure. Pause here. Voila. Gradually you see it evolving to a structure that is highly organic, but still perfectly meets the manufacturing constraints of your die casting process, so that you can benefit from the flexibility your manufacturing process actually offers, instead of putting just regular fins and straight fins in here, but still making sure that it doesn't come at an added cost when you put this in production. Now, a few things you can notice when you look at the design. And so it looks highly organic, looks maybe almost random, but the full process is driven by the physics that are actually ongoing in this product. So if we, for instance, look at this heat source underneath my mouse pointer, this heat source is actually this electronics module. It's cooled by these pin structures that you see here in the middle, the top middle of this part. Now these pin structures are characterized by a high heat transfer coefficient, and the boundary layer is continuously broken up. High heat transfer coefficient, but it comes at the cost of a higher pressure drop. Now that higher pressure drop obviously would, if you would not take that into account, that higher pressure drop, it would penalize your operating point of the fan. So what actually happens is that ColdStream will add this wide open channel afterwards to make sure that the overall pressure that the fan here on that the fan sees is limited, so that the flow rate is still sufficiently high to provide sufficient cooling capacity to these cooling structures. On the other hand, on the other side, story is a little bit different, because you have two heat sources to cool. First one, a bit similar as the one in the middle, pin kind of structures, followed by an open structure to make sure that the pressure is balanced. But after to cool this last heatsink, you'll see that on top of it are these very long, elongated, stretched fins, and basically creating a low pressure drop, much more contact area, and that is to counterbalance the fact that if the pressure would drop over these fins would become too high, the air will actually, and the air that comes from this first fan, if the pressure drop over these fins would be too high, it would take a detour into that big wide channel. But by making the choice to limit it to long fins, you actually see that the flow distribution is exactly the way you would like. And with this kind of structure compared to regular fins, you gain easily around 15-20% in thermal resistance. And so I hope everyone understands and that I managed to convey the message that this kind of process, the real power or that is used to get to these additional performance gains are fully based on the physics that are ongoing and controlling the physics. And that translates, obviously, is a direct translation, obviously, of the gigabytes of simulation data that is used internally to train that model, to train a model that understands what are the physics that are ongoing and how can they be controlled for the better use. This was an example for air cooling, for die casting. All the way on the opposite spectrum, you have, for instance, this 3D printed 3D printed liquid nitrogen cooler. This is for chip cooling at minus 200 degrees Kelvin. Sorry, minus 200 degrees Celsius. So basically, this copper, let's say jar is filled with liquid nitrogen. The liquid nitrogen starts boiling, and it's these structures that's here at the bottom side, these tree-like structures that will take care of the optimal heat transfer to the liquid nitrogen. At the back side, you also see a snapshot of what the input looks like in ColdStream. So you see that the starting point for ColdStream is very, very simple cylinder. So again, as a user, very straightforward to get started with, but the outcome, a very complex structure that is perfectly 3D printable. And this part, we actually have the prototype here at our office. There are also a number of YouTube videos where this part is actually tested and proven to work very well. And this is most probably the most powerful passive heatsink ever designed in the world. It outperformed what was the industrial standard by a factor of 3 in cooling performance last year. On the right-hand side, you see a number of variations, and the main message I want to bring there is there's no limit to the variation you can put into it. So whether it's very small components or very complex 3D printed structures at the top right, cooling jackets, and electronics cooling with natural convection, or just flow manifolds that that need to be optimized. All of that perfectly fits within the scope of the technology we have developed. So that was for 3D printing. Again, if we switch to do a different manufacturing technique, we keep all the models the same. Optimization engine or the generative design engine remains the same. The only thing we switch from 3D printing or die casting to sheet metal forming. Again, we open up a completely new line of products that you can start optimizing. And in this case, for sheet metal forming, you can quite easily design battery cold plates that are used to cool batteries in EVs or in hybrid cars and so on. So just a few clicks of the button and your power inverter design tool has switched to a battery cold plate design tool with exactly the same workflows and so on. The only thing, as mentioned, that changes would be the specification of your manufacturing constraints, and that's basically it. So you see here as well variations on regular dimple structures to highly organic, highly complex structures that see that again fit perfectly within the scope of your very often your very complex manufacturing constraints in this case. Well, then two more examples, and then we can open up the floor for questions. I want to be very respectful for the time here. So air-cooled electronics, it's just a very simple comparison, and the story is always the same. You have set the boundary conditions, you set the materials, you specify what the target is that you want to achieve, and then you let the computer do the heavy lifting for you, and you see that the simple serpentine channel can basically be replaced by an organic structure like you see here at the top, where you can gain easily 20% of performance and 60% in pressure drop for uniformity that also goes up then by more than 15%. Same story here for an inverter cooling. So these slides will be shared after the webinar, if I'm informed correctly. So also the links to the case studies, you will find them where you can double check the statements that I make here. For the same thermal performance, saving 25% or 24% in pressure loss, while keeping your engineering time, your human time in less than 30 minutes, perfectly within the scope of what the technology can offer to you. Voila. So that said, message I wanted to pass was, okay, it's one platform, but the possibilities are basically endless to what you can do in the field of thermal management. I gave a few examples on air cooling and liquid cooling, on regular, let's say, on flat geometries, but also e-motor cooling, on curved geometries. All of that is perfectly perfectly possible. Topics we didn't touch yet or didn't touch in this webinar, but please reach out in case that would be of interest as well. Our heat exchangers, manifold designs, or a very in-depth CPU and GPU coolings. But feel free to reach out on those topics as well if they would be of interest. Well, that said, I'm more than happy to open up the Q&A. I'm going to pass the floor again to David, and if you have any questions, don't hesitate to put them in the chat.
Yes, thank you very much, Lieven, for the comprehensive presentation. And I think this also showcased what are the possibilities with respect to ColdStream, in what many different areas can be applied to. We do have some questions up for you. So one of them is a question with respect to targets. So the question is, can you set multiple targets, concurrent targets, for mass, pressure drop, and temperature performance?
Yeah, well, excellent question. Obviously, I find it excellent because the answer is yes. Yeah, so we have indeed more than 20 objectives and constraints available within ColdStream, and they can be combined however the user sees fit. And so obviously, the more constraints you make a design process or more targets you add, the more complex and a design process more complex the design process would become. So it might take a little bit longer to evaluate, but it's perfectly possible to combine a temperature minimization with a pressure minimization and a mass minimization to find say a proper working point that suits all three objectives. Obviously, to make that choice on what is the best, what's most suitable, that's where the engineer obviously comes in again with their expertise.
Perfect. Thank you for explaining, and I hope this answers your question. The second one is, in ColdStream, can you go straight to custom designs, or is it necessary to go through the standard designs first?
It is highly recommended to go via the standard designs. So this technology that we have developed is extremely powerful, if you ask me, but in some cases might be sensitive to local minima. That's unfortunately one of the side effects if you work with highly nonlinear Navier-Stokes equations that not always behave the way you would initially anticipate on. So one way that you can very easily avoid that or minimize that chance is to first go through the standard design process. Chances are very big that you actually can find already a suitable design for you with the standard designs, that you actually don't need those custom designs. But if the standard designs are not, let's say, do not meet your targets yet, then taking your best performing best performing pins or fins design, for instance, as a starting point for a custom design, will actually speed up the second process and will also help to avoid these local minima. So it's not necessary, it's highly recommended, and obviously this is where our support team and also the team of in Summa is ready to help and to support the users in the best to give them the best experience.
Yes, thank you, and I hope this answers your question. One of the other questions is for the simple serpentine cold plate optimized to organic design, does the software consider raising manufacturing requirements?
Yeah, so manufacturing requirements are always needed, and so we cannot simply say make now something and you disregard any manufacturing constraints, because you might end up with a design that requires nanometer size channels or something like that. So also for serpentine cold plates, a minimal manufacturing input is needed, but in case of serpentines in particular, that input is really minimal, as in the only specification that the user needs to make is what the minimal channel width is of the serpentine, just to avoid that if you're designing let's say, a battery cold plate with a serpentine, that you end up with a channel that is has a size of less than a millimeter in width for a cold plate that is maybe 2 or 3 meters in length.
Yeah, exactly. And I hope this answers the question as well. And also, there is one on the CFD side. So the question is there a mesh-based CFD solver in the background? And can you choose the number of degrees of freedom and check the mesh?
Yeah, so there is an so the backend simulation engine is based on OpenFOAM, so it is mesh based. The meshing, let's say the meshing is, sorry, for the biggest extent fully automated in ColdStream. The user has but the user has some controls over it. So the user can control the resolution levels. Typically we express it then in, let's say, draft, conceptual, or detailed level. The reason why it is fully automated is, on one hand, it's typically a burden to create a highly qualitative mesh, and so that's where we see that algorithms that we developed are outperform typically the human skills. On the other hand, the mesh is also tightly connected to the designs that you create, so it is almost a necessity to fully automate that in the backend. So there is a control. Once the mesh, there is some control over it. Once the mesh is created, it is already available for inspection by the user. It also comes with a number of let's say quality fields like non-orthogonality, skewness, and so on that the user can visualize and verify that it meets their requirements. But it is not fully open to full customization for the simple reason that it's simply that it's not possible to do that in combination with creating unknown designs yet.
Yeah, and yes, and I hope that this answers the question. One of the other ones is related to dynamic cycles. So can you, for instance, run an optimization for a dynamic cycle, something that shows like the best overall performance?
Yeah, so we have, let's say, we have methods to help bring that to an equivalent steady state condition that is then usable for the design cycle itself. So a full dynamic load, like a cyclic heat load or something like that, imposing such a thing as an input for the design process is not possible. That technology simply doesn't exist yet to take that into account, or would be extremely expensive if we would apply it today. But we have developed over the course of time some methodologies that help to translate that into an equivalent steady state condition that can be used then as an input to the design process.
We still have time for 2 questions. Thank you for your answer. So one of them is, can you optimize a moving heatsink? Is that a possibility in the software?
It depends on what you mean with moving. So I also see part of the questions are about a rotating heatsink. So if the heatsink is indeed in a rotating frame, that's possible. It's perfectly possible to take them into account. So there is support for multi-reference frame simulations. So a typical example is, for instance, the rotor of an electric motor that is embedded in housing. Then you can perfectly design redesign the rotor itself, or the outside of that rotor. So based on what I see in the question, my answer will be yes. If the heatsink is rotating, it's perfectly feasible to design for that.
Yes, thank you, Lieven. And then the final question is, do you validate the outputs with repeatable CFD tools like ANSYS Fluent, or is this expected to be done by the customer?
It is expected to, well, put it this way, it's expected that the customer believes our results, because we believe the results. So I think everyone can imagine here in the call that over the past 10 years, we did several cross checks with ANSYS Fluent, with Star CCM, and several other tools as well, also from Hexagon the Cradle CFD, just to make sure that the output that we generate is consistent. Again, the simulation engine that we use is based on OpenFOAM, so it's not something we have built from scratch ourselves on that part. But to make things easier, so for those customers that do want to do or do need to do that double check for internal approval or internal qualification, there are a number of export options available as well to export in, for instance, to Ansys Fluent, also to OpenFOAM, and some others as well that help with that process. So we don't validate it proactively. We don't expect the user to do that, or we don't see the direct necessity to do that, because we know from past experience that the CFD engine is as accurate as what you can expect from a CFD engine in 2025. But we do make it easily accessible if users want to do that.
Perfect. Thank you for the answer, Lieven. If you have any questions, please feel free to send us an email, either to Lieven or to us. By this, we would like to close this webinar. Thank you for your attendance and hope to see you soon.